So welcome to the Pioneering Proofs mini-series about deep learning or neural networks. In this part, which is part 1, we are going to discuss the Jacobian chain rule. And this is going to be used for understanding gradient descent. So yeah, I'm really excited for this one, and let's get started. So we begin with case 1, which is the simplest case, in which we have a scalar y is equal to a function of vector z, where vector z is of length m, and z is equal to a vector function of vector x, which is of length n. So by the multivariable chain rule, we have that the partial derivative of y with respect to xi, where I is the ith element in x, is equal to the sum over j of the partial derivative of y with respect to zj times zj by xi. So this is the multivariable chain rule for the ith element in x. And what we're doing is that we're summing up all the possible paths from y to x through the intermediate variable z. And if you need to review the multivariable chain rule, then I suggest ChatGPT or the internet or YouTube. And let's proceed. So whenever we have a summation of two things multiplied together, we can do matrix multiplication. So here we have the equivalent form of our summation in matrix form below, where we expand I into a row, and yeah, we multiply the row vector by the Jacobian matrix, partial derivative of of z with respect to x. That forms the Jacobian matrix on the right, and the result is a row vector. All right, so now we move on to case 2, which is a bit more complex. We add the intermediate variable w, where w is a vector of length n, and we change the lengths of vector x to length p, and then z remains as length m, y remains as a scalar. And so in this case, we're adding up all the possible. So if we want to take the partial derivative of y with respect to xi, we're going to add up all the possible paths from y to xi in the chain. And so we can do this by taking the double summation of j and k of the partial derivative of y with respect to zj times the zj by wk times wk by xi. So that represents all possible paths through intermediate variables z and w from y to x. And once again, we can represent this in matrix form. And in that bottom box, in the parentheses, you have a row vector multiplied by a Jacobian. A Jacobian is just a matrix of partial derivatives. And if you do that, then you get a row vector, and within each row you get a summation, and you multiply that row vector by the vector to the right to get the left-hand side of the equation. So the general case of adding all the paths from y to x through all the intermediate variables z, z1, z2, z3, z4, all the way to zq minus 1 with index variables I1, I2, all the way to iq minus 1. We get that. So there you have it. That's the general rule. And of course we can express this in matrix form, which we'll do next. And here we express the general case in matrix form. And as you can see, if we evaluate the parentheses, we get row vectors multiplied by matrices to the right, row vector multiplied by matrix to the right, and so on until you get to the target variable x. Yeah. Alright, so we can represent the gradient partial derivative of y with respect to the vector x with the multiplication of Jacobians until you reach your target variable x. Alright, so thank you for watching and have a great day. So in this video I actually had to delete it from my channel twice. I had to delete it twice from my channel because I made a few mistakes, and I'm kind of getting obsessed with it because like I keep on like uploading it, then deleting it, then uploading it, then deleting it. But this iteration should be my best, should be my final iteration, and I hope that you like and subscribe to my channel. Sorry, like the video and subscribe to my channel and not like the channel. I mean, you could like the channel if possible, but I don't know if there's an option for that, but that'd be cool. Alright, so I guess that's it. Goodbye, and have a great day.